Row reduced echelon form and rank. In this video lecture, we'll try to understand what we mean by row reduced echelon form, or in general we call it only echelon form, and then we'll learn how we can actually determine the rank of any given matrix once we have the echelon form of that particular matrix. So suppose we have a matrix A which has in general entries Aij, which has m rows and n columns. Then this matrix A can be converted into its echelon form by using the fundamental row operations. We'll talk about the fundamental row operations later. Once we use the fundamental row operations and we convert this matrix A into a matrix which has the following two properties. The number one, the leading entry in each non-zero row is 1, and number two, each leading one is the only non-zero entry in its column. So if any matrix which satisfies these two properties, then this matrix is in the echelon form. Initially, a given matrix may not be in the echelon form, but by using the fundamental row operations, we can convert any given matrix into its echelon form, and it will be in the echelon form when it satisfies these two properties. So we'll learn via an example how we can convert a matrix into its echelon form, but to convert any matrix from its initial form to echelon form, we need to learn what is the fundamental row operations. So let's see the fundamental row operations. In reality, there are three fundamental row operations. If we go one by one, the number one is the addition of a multiple of one row to another. That is, if we are having two rows R1 and R2, so if we replace R1 by R1 plus alpha times R2. So this is the first fundamental row operations. It says the addition of one row to the scalar multiple of the another row. And the second one is the scalar multiple of any row. The second fundamental row operation is the scalar multiple of any row. So we can replace the row R1 by a non-zero scalar multiple of the same row where lambda is non-zero. So this is also a fundamental row operation. And third one is the swapping of two rows. If we replace the row 2 by row 3 and row 3 by row 2 in any matrix, so it will remain in a particular form, and this particular operation will be called as a fundamental row operations. Fundamental row operations have an immense amount of importance in the matrix, because once we apply the fundamental row operations to any given matrix, so the resultant matrix actually preserves many properties of the initial matrix. So these are the three fundamental row operations which can be used for the conversion of any matrix into its echelon form. Now we'll do an example where we'll convert a given matrix A into its echelon form. So let's take a matrix A which has the entries 1 1 2 1 1 2 1 1 and 3 4 5 3. So definitely this matrix is not in its echelon form because the leading entry in each non-zero row is not 1, and the each leading one is the only non-zero row entry in its column. So both the properties are not true here. So what we'll do, we'll use the fundamental row operations to convert this matrix into echelon form. Sometimes these operations are also called as a Gauss-Jordan elimination operation. So let's apply some operations on this matrix A. So if we carefully observe this matrix, so the third row is actually the sum of 2 times sum of the first row and the second row. What I mean to say, if I use this operation where R3 is replaced by 2R1 plus R2 minus R3. So it is actually the combination of what we stated as a fundamental row operation. So what we'll get all the entries as 0 in the third row. Further, we can apply one more fundamental row operation in this matrix for second row, and the second row R2 is replaced by R2 minus R1. So it is 1 minus 1 0, 2 minus 1 1, 1 minus 2 minus 1, 1 minus 1 0, 0 0 0 0. So now see here, now if we try to convert this entry into 0, what will happen? In that case, this entry will become non-zero, and then it will be the violation of the second condition which we stated as a row reduced echelon form. So this matrix is actually in its echelon form where the leading entry in each non-zero row is 1 and each leading one is the only non-zero entry in its column. So further, if we try to do anything in this matrix by using the fundamental row operations, then it will not follow the above listed two properties. So this matrix A was initially given, and by using the fundamental row operations we converted this matrix into its echelon form. Now with the help of this echelon form we can give a definition for the rank of a matrix. So rank of a matrix it has many definitions, but it can also be defined with the help of the echelon form. So suppose A is a matrix A, then rank of A is the number of non-zero rows in its echelon form. So if we try to check this definition to this previous example, so say we wanted to know the rank of this matrix A. So we already have its echelon form. So what definition says? The number of non-zero rows in its echelon form. So this is the echelon form, and we can simply count the number of non-zero rows. The number of non-zero rows are 2, the first one and the second one. So the rank of this matrix A is equal to 2. So in this way, this row reduced echelon form in one of the way is helpful to determining the rank of any given matrix A. The best part for this method is it doesn't depend on the order of the matrix, whether it's a square matrix or a non-square matrix. We can always be able to determine the rank of any given matrix irrespective of its order, whether it is a square matrix or a non-square matrix.